Let's get started.
Okay, so do I introduce myself, or do people kind of know who I am?
Yeah.
People knowing?
Somebody can introduce you.
Go for it.
Okay, so I'm going to go ahead and shut the lights off then. Is that good? Or
Yeah, let's see how it.
That's good. The front lights off.
Yeah. Okay. All right. So I'm Randy Leffler, and today I'm going to be talking about studying the properties of SF6 gas mixtures for directional dark matter detection. And this is going to be the outline for my talk. First, I'm going to define some terms that I'm going to use over and over again throughout my talk, so that you guys are familiar with them and they're clear. Those are going to be discrimination, directionality, and fiducialization. And then after I've defined those, then I'm going to give evidence for dark matter, and I'm going to describe direct detection techniques for dark matter, and then the leading directional dark matter experiment, drift. And I'm going to talk about some drawbacks of the drift experiment and how that motivated the research that what I'm going to talk about today, motivated my research. And so I'll talk about the search for an ideal gas for a WIMP TPC, and how we focused on SF6, and I moved forward that work by measuring discrimination and directionality, utilizing a 1D readout in a low pressure SF6 TPC. And then I'll talk about how in SF6 there's an issue of fiducialization. There's a low fiducialization efficiency, and that will motivate the next thing that I'll talk about, where I search for how to enhance this fiducialization in SF6. And in doing that, I discovered something really, really awesome, and I was very excited about that, and I did a lot of different experiments about that. But ultimately, what I discovered solves the issue of the fiducialization. And so I'll talk about that. And then I'll look at a particular mixture, that solves this issue, where I add 20 torr CF4 and 3 torr SF6. This mixture, I'll measure the discrimination and directionality in that mixture. Okay, so it's 9, 10 right now. Okay, so some the key terms that I want to define. The first one is discrimination, which is the ability to identify interacting particles in your detector. So that's discrimination. And then directionality, or sometimes I'll call it skewness, is the ability to measure the direction of the recoil in your detector. And then fiducialization is the ability to localize where in your detector the event occurred. Okay? So, there you go. All right, and then next, what is dark matter, and why do we think it's there? So I have this slide for that. So here's a galaxy, and this is a picture of the orbital velocity of stars and other objects about their galactic center. That's this curve here. And what we predict, or what we expect, is that beyond the visible disk of the galaxy, the orbital velocity of these objects should decrease. But what we measure is this here, these flat rotation curves. And this discrepancy here between these two curves, a solution is to say that this galaxy is immersed in this hidden matter that provides this extra gravitational attraction that sustains these orbits at these high velocities and large radii. And so this hidden matter is called dark matter. Yeah. Okay, so with that, with those measurements and other measurements, we get this understanding of the universe that ordinary matter and baryonic matter that we're made up of is only 4.6% of the universe. Dark matter that I'll be talking about today is 24% of the universe, and then the rest is this mysterious dark energy. But I'll be talking about this dark matter fraction. Okay, so there are people have lots of different ideas for what dark matter could be. This shows kind of how what the field is like and all the different ideas. But I'm going to be focusing on this weakly interacting massive particle dark matter candidate, which is or WIMP, which is well motivated. So when I say dark matter, or I'll be referring to WIMP dark matter. And so there are several different ways to detect these WIMP particles. One is production technique, another is indirect detection, but what I'll be focusing on is direct detection. And for this, you have a dark matter particle enter your detector and interact with some ordinary particle, some standard model particle, and the dark matter recoils away, and the standard model particle recoils through your detector and deposits some energy in your detector, and it's this standard model, that energy that's deposited, that you observe. Okay. So specifically with direct detection, I'm going to be talking about the directional direct detection, where for this, the signal that we look for is this daily or sidereal modulation, and that's depicted here. So here is here's the Earth, and as it's moving through the galaxy, it's moving in the direction of the constellation Cygnus. And if our galaxy is immersed in a halo of dark matter, what that would mean is that the Earth, as it moves, would be feeling this WIMP wind move across the Earth, and that's these here. And what this would do is that if you have an earthbound detector, the WIMP wind would cause recoils in your detector at this time here to be preferentially downward into the Earth. But at another time later, for example 12 hours later, they would be directed preferentially into the wall of the detector. So what this means is over a day, you would notice a modulation in the direction of nuclear recoils, in your detector. So that's the signal that these direct detection or directional experiments are searching for. And I'll talk about the leading directional experiment, or the drift experiment. And it is a 1 cubic meter time projection chamber, and I'll describe what that means in a second. But it's operated with in a gas mixture with these three different components, and I'll describe what the importance is of each one. But I want to focus on this component here, the 10 torr CF4. That is the target for the spin-dependent WIMP interaction, and specifically fluorine is the target, the sensitivity to dark matter, and so that's that. And then here's the drift experiment. You see that there's this central cathode in the center that divides the detector into two regions, and then there's this uniform electric field within each side, and so what happens is that imagine this is one of the gas volumes inside of the detector, and so here for example a WIMP particle or some other particle, but here I show it for a WIMP particle, interacts in that gas, and it causes interacts with a molecule in that gas and causes a nuclear recoil, or an atom to recoil through the gas, and as it does that, it leaves behind along the recoil a trail of ionization, and the electrons are, what drift does is it takes the electrons, and instead of drifting them in the electric field to the readout would be over here, and there's a uniform field. Instead of drifting electrons, it has this CS2 component of the gas mixture. CS2 is electronegative, so what it does is these electrons are captured by CS2 really quickly, and there's these, what it's drifted are these CS2 minus negative ions to the readout. And the reason to drift negative ions instead of electrons is because you get this low diffusion without magnetic fields. traditional like time projection chambers, you need a magnetic field to get low diffusion. And then also I want to point out that in these low pressure gas detectors, these nuclear recoils are typically a few millimeters. And remember, I said the experiment is a 1 cubic meter, so we have like millimeter sized tracks inside of a 1 cubic meter detector. So these are small compared to the size. And then lastly, I'll point out that the drift velocity of these negative ions as they drift to the readout is much slower than the electrons as well. They're actually about 1,000 times slower than electron drift. Okay? All right, so that's that. But like I said, there could be other particles that interact in your detector, not just WIMPs. So there could be other backgrounds. So it's important to be able to reject them or do this discrimination that I mentioned. And the most prevalent background are these gamma ray induced electronic recoils. And the way you do the discrimination for them is nuclear recoils have the property that they lose this dEdx is the energy loss along the track, and nuclear recoils lose more energy per unit length than electronic recoils. And what that means, at the same energy. So what that means is if you plot the range versus energy of your events, the electronic recoils will tend to reside in this vertical band here. So at the same energy, they tend to be longer than the nuclear recoils. So what you can do is you can separate the two populations, and you can do your discrimination that way. So this is very important, and I'll be talking about that more. And then the next background I'll talk about are these radon progeny recoils, or RPRs. And what they are is they're the alpha decay of radioactive elements, where there's a recoiling daughter nucleus through your gas, and so they're like heavy nuclear recoils in your gas, which means that in that range versus energy parameter space, they would reside in the nuclear recoil band. Okay, which means that for the they look like WIMPs. So they're a troublesome background, and you can reject them or suppress them using a few different these two means. You can use ultra pure detector materials, but that can only get you so far. You always have contamination. And then the next one that you can do is you can fiducialize your detector, that other term I was mentioning. And for the drift experiment, what they do is they add this 1 torr of oxygen to their gas mixture, and when they do that, their signals look like this. So this is the primary CS2 minus negative ion part of their signal, and when they add oxygen, they get these minority species here that show up. So what you can do, and what fiducialization is based on the relative timing of these peaks with the primary peak, you can derive where along the drift dimension the event occurred, and I call that Z. And if you can do that, you can then reject events that occur at the cathode or along the walls, and then that's where these a lot of these RPR events will occur. So you can reject them in that way if you can't fiducialize. So again, fiducialization is very important, and I'll talk about that a lot more. But here's some drawbacks for the drift experiment, and so the obvious one is that it's at low pressure, which means that there's a low target gas for WIMPs to interact with, and again, this is the mixture that the drift experiment uses, and you'll notice I said that the CF4 component of the gas is specifically that's the target for WIMP interactions, and it's only 10 torr. It's only a fraction of the whole mixture. So ideally, we like to operate in a gas that uses that does all these things, does the fiducialization and all these things in one thing. Remember, I needed to add this CS2 component to have that negative ion behavior. That won't happen in pure CF4. Okay. So lastly, there's this the CS2 is toxic, and it's difficult to handle. They've been able to do it, and they've been successful, and they can do it. But if we could find something that wasn't toxic, that would also be beneficial. So that led to some work at our group where we were searching for an ideal gas for a WIMP TPC, and we started looking at SF6. And so SF6 has been studied extensively as a quenching gas because it's